We're going to take a few sections of Chapter 7 and study those for Fourier series transformations. We are not going to go into the complex formulations of series, but we will look at how discrete Fourier transforms are performed in MATLAB, as well as fast Fourier transforms and their impacts on modern computing systems. And it's a very, very common and powerful tool for spectral analysis in signals. So let's look at the textbook. And starting in Chapter 7, they go over a background of Fourier series. If you've never seen this before, it can be handy to look at. And several in the class hadn't seen this before, so I want to go straight into the first example of what a Fourier series does. It allows you to take some target function. In the algebraic sense, this is what a Fourier series does. It allows you to take a target function and then with a series of sine waves of ever-increasing frequency. Now, I'm kind of combining sine and cosine waves again because they are really just the exact same type of wave with a phase offset of 90 degrees, right? If you look at the shape, it's exactly the same, just offset a little bit around the unit circle. So with only one wave, that's about the best fit you're going to get for the target function. With three distinct waves, you can get a little bit closer, but still there's significant oscillation. With six, ever so closer, and this trend continues. In practice, you always start approximating closer and closer and closer to the target waveform, but never actually achieving it, especially in these corners where you get those high-frequency oscillations that keep the Fourier series from exactly matching the underlying function. What this looks like in two other visualizations, when you take each individual contribution of the series that ended up making these square waves appear up top, you can see that not only are the frequencies increasing, but we are tuning the relative strength of each wave so that whenever they're combined, you end up getting the shape that you want. This can be looked at in a frequency domain by looking at the spatial frequency, that's the spectral frequency, versus amplitude of each contribution. So the first term, second term, third term, fourth term, etc. And that is basically the gain applied to the sine or cosine wave of that frequency before they're superimposed. So by setting these gains precisely, mathematically you might say, you can just turn ordinary sine and cosine waves into any periodic function of your choosing. I should say an approximation of any periodic function of your choosing. So the very classical form of Fourier series is shown here. The infinite Fourier series shown mathematically. So from k equals 0 to infinity, you would have two terms for each k. You have a gain A and a gain B applied to the same sine and cosine forms, which are pi k of x over L. For both sine and cosine, same form there. So k increases in integer forms. X is the x location of the function, as always, and L is the interval that the function is calculated on. Now, L is actually the interval divided by 2, so it's half the length. Keep in mind that's an important distinction to make. Thankfully, for the general infinite Fourier series, you already have solutions found for determining A sub k and B sub k. So all of the unknown A and B gains can be determined by executing this formula and finding the series solution that tells you what every single gain should be, from 1 to infinity. Also, you obtain this term B naught. That is the singular gain for the B term that actually kind of takes care of the DC case, the zero frequency average value of the function. If you're interested in the derivation of how you arrive at those formulas for A and B, you're welcome to read this page on chapter 258, but really this is a practice type component of the course, so let's get right into that example. I'm just going to use the example from the book because it's as good as any. So starting with this periodic function, step function from -1 to +2, that goes from -1 to 0 in the x-axis, and then from 0 to +1 for the higher value. So this is a periodic step function, just alternating back and forth between the value of -1 and +2. So the domain starts at -1 in the x dimension and ends at b of 1, so that means that our total L length is 1. That's that is the first thing you should probably determine. We'll be applying this to, of course, the general infinite Fourier series. That formula will be the same for every Fourier series problem you do in the general infinite sense. So then you just start applying B. This is actually B sub k, but they gave the subscript m, I think, just to distinguish. B naught, and then A sub m. If you determine those three coefficients, or really they represent a series of coefficients, then you have adequately formed the representation of that function. So here for b sub m, since we do have a piecewise function split into two pieces from -1 to 1, we actually separate that into two different integrals. The left-hand integral handles the region from -1 to 0, where the function is valued at a constant -1. The right integral handles from 0 to +1, where the function has a value of 2. So this overall integration, once you perform it, coincidentally comes out to nothing. So all this separation, all that work, for nothing. If you look at the endpoints, it becomes fairly apparent. So if you integrate cosine, you end up getting sine. So then with an endpoint at 0 and an endpoint at -1, you would have sine at an x value of 0 with an integer multiple m. So any multiple of 0 or pi for sine is 0. And the same thing happens on this second integration where you go from 1 to 0. It's the same problem. You integrate cosine, you get a sine term, which turns to 0 for every integer multiple of pi. So this periodicity of the sine and cosine functions in Fourier series can end up making, especially for some academic cases, it can make it where most of these coefficients end up being nothing at all. So the convenience here is that the entire b term goes away. So the cosine contribution of everything in this periodic sine wave function is gone. That's nice. So for b naught, this is the one exception. This is one you should always check by itself because, like I said, it represents the DC gain value. That's 1/2 times L, or 1 over 2L really was what we're looking at. L has a value of 1, so it doesn't really change. And again, they split it apart into a region from -1 to 0 and 0 to +1. So you integrate the -1 functional value on the left-hand side in the negative region. You integrate the +2 value on the right-hand side. You combine it, typical integration, you get a value of 1/2. Now, it is not a coincidence at all that 1/2 happens to be the average value of the function. So that's essentially, if you think about it, the center line of this square wave, going right through 1/2. So that is what the term b naught does. It centers the sine wave you'll otherwise be oscillating about the point b naught. So the only term that ends up being a true series in this example is the a term, a sub m. So again, just following the formulaic result for a sub m, again splitting it into two regions for the two distinct values of the function we're dealing with, namely -1 and +2. You go through and execute the integrations. So over here, you actually get sine integrating into negative cosine, and it expands out to create a 1 in the case of 0. So here, a negative cosine term at 0x for all values of m, then, for the integrated cosine term, would end up being 1. No matter what m is, it's multiplied by 0, so it will always be cosine of 0 degrees, so that's where the 1 comes from. Subtract off the x value of -1, and that generates this second term. The same exact form happens on the second integral, except you're doing it with a different valuation of the first function, so that it becomes 2 over m pi. That m pi is just a remnant from the integration of the sine into cosine. You, of course, take the interior terms and take their coefficients and put them 1 over the coefficient out in front. So then you combine those terms into a 3 over m pi parentheses 1 minus -1 to the m. And that term confused me at first. But if you think about it, -1 to the m is the accurate representation of cosine pi m. So for the case m equals 1, you'd get cosine of pi, so that would be -1. M equals 0, cosine of 0 would be 1. Cosine of 2 pi, +1, 3 pi, -1, 4 pi, +1, 5 pi, -1. This produces the same series. -1 to the m, as m is a series of integer values, just alternates back and forth between positive and -1 for every value m. How handy is that? Of course, m is not equal to 0. I think I threw one of those cases in there. Whoops, my bad. So this is the solution for all of your a sub m values. That is the series solution for all of the coefficients you care about, the infinite set. B of m is 0, b naught is 1/2, so you plug all of this into the final solution form, and this Fourier series summation represents the approximation of that step function in completely sinusoidal terms. Now they've done us the nice benefit of showing a few graphical solutions of an increasing number of terms. So with one term, you basically just get a sine wave. It's bad approximation. As you can see, it increasingly becomes more accurate to the source function, but even with 50 terms, you still have significant oscillation, especially at the hard edges and hard turns associated with the corners of that step function.